Okay, yeah, please. Whenever you're ready.
Okay, so thanks a lot for the invitation. And my talk is about the so-called Hkd geometry. So Hkt means hyperkähler with torsion. And this is a special kind of geometry on hypercomplex manifolds. And more or less, the research consists in finding a special metrics on hypercomplex manifolds, which are more general than the hyperkähler ones, and putting some restrictions on the torsion. So I start by definition of hypercomplex manifold. It's just a smooth manifold together three complex structures. So M is a smooth manifold. And I, J, K are complex structures. And they satisfy a quaternionic type relation. So the real dimension of M is equal to 4M. And the ijk satisfy the usual quaternionic type relation. Ij is equal to minus ji is equal to k. Okay, and the basic example is given by h to the n, where h is the quaternionic vector space. And this can be identified with R. For n, together three complex structures, which are considered canonical, which here I denote by I0, J0, and K0. Okay, this is the basic example of hypercomplex manifold. Now I recall the definition of the Obata connection. So on a hypercomplex manifold, so there is always a unique connection nabla, which is called the Obata connection. So which satisfies the following conditions. So the first one, it preserves the three complex structures. So we have nabla I equal to nabla J equal to nabla K equal to 0. And it is torsion free. Okay, and here, as basic example, we can consider an hyperkähler manifold. So we take M, I, J, K, G, hyperkähler manifold. So here we have this is hypercomplex manifold. And G is a Kähler with respect to IJK. Okay. In this special case, nabla is equal to the Levi-Civita connection of G, since it is torsion free and it preserves the three complex structures. Okay, but in general, we don't need a metric in order to have the Obata connection. And the Obata connection can be used in order to have information about the geometry of the manifold. For instance, if R nabla, so if the curvature of the connection is 0, then this is equivalent to require that the hypercomplex manifold is locally isomorphic to the standard model. Okay, this case is the case which is usually called the locally flat case. This locally isomorphic means that we can find locally some coordinates which are holomorphic with respect to each complex structure, so each ijk.
Luigi, can I ask a question?
Yeah, of course.
Is there like a causal formula for this Obata connection?
Sorry, say it again.
Like, can you just explicitly write down the Obata connection using the complex structures?
Yes, you can explicitly. Yeah, there is an explicit formulation for the Obata connection, and yes, can be written explicitly in terms of the three complex structures. Yes, there is an explicit formulation. Yes. And another interesting condition is when the holonomy of the Obata connection is contained in SL and H. So these are matrices n times n, having in entries in H, having determinants equal to 1. And this condition implies that the canonical bundle of M and I, or also another of the three complex structure, is holomorphically trivial. Okay. The converse is not true in general, but it's true. In the Hkt case, which I introduce a little bit later. And if when this condition is satisfied, the manifold Mij is called a SLNH manifold. So when I say about SLNH manifold, I mean that the holonomy of the Obata connection is contained in SLNH, and this implies that the canonical bundle of one of the three complex structure is holomorphically trivial. Okay, and now I can recall the definition of hyper-Hermitian manifold. And of course, this is the natural definition. So we have a hypercompass manifold together a Riemannian metric G, and G is Hermitian. With respect to each complex structure ij. So this is something which is more general to the hyperkähler case. Okay, so in this situation, of course, we have three Hermitian structures: Ig, Jg, and Kg. And of course, each one induces a fundamental form, omega I, omega J, omega K. And then by using these skew-symmetric forms, we can construct a form which is usually denoted by capital omega, which is by definition given by omega J plus I omega K. And since I and J anticommute, we have that this form is of type 2-0 respect to I. Okay. This form has two nice properties. So the first one is that this form is satisfies a condition which is usually called the condition to be Curial. This means that if you consider omega bar, this is the same of doing J of omega. So where the action of J on two forms is the canonical one. So J omega of xy is by definition omega of Jx and Jy. So this is the first property which omega satisfies. And the second one is that omega is positive. In the sense that if we do omega of z j z bar, this is positive for every z vector field of type 1,0 with respect to I. So remember that I is the first complex structure, Yj is the second complex structure. So it satisfies, so is real in some sense, and it is positive in some sense. So what we have is that the metric G induces this for omega of type 2,0 with respect to I, which is Curial and positive. Okay, and also the converse is true. So if we have omega, which form of type 2,0 with respect to I, which is Curial and positive, then omega determines a metric G. Okay, so there is a one-to-one correspondence between hyperemission matrices and this kind of skew-symmetric forms. So this bijection is analog to the one of Hermitian matrix and the fundamental forms in Hermitian geometry. So it's very natural to consider a hyper-Hermitian metric special if its form capital omega satisfies some condition. And now I can give the definition of Hkt manifold. And this is a definition which was introduced in physics by Owen and Papadopoulos. And then it became intrinsic also in mathematics and in geometry. And the definition is the following. So start with an hyperemission manifold. Okay, so as before, I consider the three admission structures. Okay, so and each Hermitian structure induces a different bismuth connection. So induces a bismuth connection. So these are bismuth connections. Okay, which in general, these three bismuth connections are different each other, but the definition of Hkt means that the three bismuth connections are the same. So means that nabla I is the same of nabla J and is the same of nabla K. Well, so this is the original definition of Hkt manifold, and a little bit later, Grancher and Poon studied the geometry of Hkt manifolds. In particular, they proved that the Hkt condition is equivalent to require that the form omega is partial closed. Okay, where this partial is computed with respect to I. So with respect to the first complex structure. So of course, this is more general than the hyperkähler case where omega is declosed. So it's also holomorphic, not all only partial closed. Okay, and I mean, these Hkt manifolds are interesting for many reasons. One of the interesting facts is the following, as I said before, for an Hkt manifold, the condition that the holonomy of the Obata connection is contained in S, L, and H is equivalent to the requirement. The canonical bundle is holomorphically trivial. Okay, so this is a result of Verbitsky. Okay, so this is, I mean, the Hkt manifolds are the central topic of this talk. Okay, some examples of Hkt manifold. So I start as usual from the trivial examples, and then I describe the non-trivial ones. So of course, we have at least two classes of trivial examples. So the first one is given by hyperkähler manifold. So of course they are Hkt, so in a trivial way, and the Hkt manifolds can be seen as a generalization of hyperkähler manifold. The second class of trivial examples of Hkt manifolds are given by hypercompass manifolds. Of real dimension 4. Okay, so in this case, any hyperemission metric is automatically Hkt for dimensional reasons. And so hypercompass manifolds in dimension 4 play the role that Riemann surfaces play in Kähler geometry. Okay, now I describe some example which is not trivial. So the first one of a non-trivial example was basically introduced by Joyce. And there is a very nice Joyce construction, and consistent consider G, which is a compact semi-simple Lie group of rank R, for instance. So, and what Joyce proved is that if we consider a compact semi-simple Lie group, it is always possible to consider the direct product between G and a torus. T is a real torus which has the dimension 2n minus R, and this number n depends on G. Okay, and M is make canonical, left invariant, hypercomplex structure, okay, this is a result of Joyce. Joyce found this example before a definition of Hkt manifolds, and after the definition of the introduction of Hkt manifolds, people observe that actually these manifolds have also an invariant Hkt metric. So, and also a left invariant Hkt matrix, Hkt metric. Okay. So another class of manifolds which give examples of Hkt manifolds is the class of nil manifolds. So which I recall they are defined as quotient of G over gamma, where G is an nilpotent group. And gamma is a compact lattice. So and Dotti Fino in 2 and 3 papers proved that some nil manifolds have left invariant Hkt structures. Okay, and they also classified a-dimensional nilpotent groups with a left invariant Hkt structure. And I briefly recall this classification because I need it later. So, and they classified a-dimensional nilpotent groups with left invariant Hkt structure. And I mean, the non-Keller ones are just 3, and they can be described in this way. So we have HR cross R3. And then there is the second model is given by HC cross R2. And the last model is given by G equal something like H times R. And here, these groups, so HR, HC, and HH are Heisenberg type groups. So these 3 groups. Are Heisenberg groups. And actually, I don't need any. I mean, I don't want to give more detail because later what I really need is that these groups give some the quotient gives some torus vibration over a torus.
Sorry, Luigi, can I just interrupt for a second? Like in this Joyce example, So you take a compact
Yeah.
semi-simple Lie group, you take a product with some torus,
Exactly.
and then you have a canonical left invariant hypercomplex structure.
Yeah.
But then, like, so is the metric a product? Oh, so yeah, it's a left invariant metric. Is it like a product with a bi-invariant metric on G or something?
I think so. Yeah. I think so, because when you consider, I mean, the idea is that the Lie algebra of the Lie group as a canonical decomposition, and then the metric makes this decomposition orthogonal.
Okay, yeah.
So I think the metric is a product there.
Okay. And then the factor on G is bi-invariant.
Yes.
Oh, okay.
Yes, is a minus the killing form.
Okay, yeah.
And actually this number n and is depends on the composition. Depends on the numbers of the pieces in the composition.
Okay.
Well, and so here there is, I mean, just also they observed that in each case, the hypercomplex structure is abelian. So this means that the bracket of I something with I something is the same, the bracket of and is the same of the bracket. So this means that all the three complex structures preserve the bracket, and later Barberis, Dotti, and Verbitsky proved that this condition is always true in every for every left invariant hypercomplex structure on an Lie manifold. So later Barberis, Dotti, and Verbitsky proved that if Hkg is a left invariant Hkt structure on an nilpotent Lie group, then this condition, which I call 1, so then 1 is always true. Okay. Okay, so the nice class of examples is given by an Lie manifold, and there are also more difficult examples, and some of them are constructed by Swan. So these are examples via construction, which is called something called a twist construction. So this is was done by Swan. So this construction is interesting because it produces some simply connected examples. And then there is a theorem, which is the Hkt version of the Boukdal-Lamarin theorem. And this was proved by Lejmi, Granchorov, and Verbitsky. So this is it's about the 8-dimensional case, and the theorem is the following. So so let I Jk be adimensional, compact, and SLNH. In this case, n is equal to 2, so and SL to H. Okay, and the result is that Mijk is Hkt in the sense that it has a compatible Hkt metric if and only if H1 of the sheaf of holomorphic functions with respect to I is even dimensional. Okay, so also this is a machine for finding the examples, and this is the Hkt version of Boudal-Lamary result. Well, this is the list of examples which usually are considered in Hkt geometry. Okay.
Sorry, when you say this Boudal-Lamary results, I guess when I hear that, I'm thinking of these results that like characterize the positive cone.
Yes, I mean that. Yeah, I mean that is a complex. A complex surface is scalar. Compact complex surface is scalar if and only have the B1.
Okay, yeah, I got you.
So this is a completely analog to Hkt geometry. When you see that, complex dimension 2 becomes quaternionic dimension 2, which is dimension 8 as a real manifold. Well, in Hkt geometry, there is also a pluripotential theory. Okay. So also this is analog to the one in Kähler geometry. So here we start with an Hkt manifold. So Hkt, and then we have the D operator, the partial operator is still with respect to I. So this goes from lambda rs with respect to I to lambda r plus 1s with respect to I. So, and then there is also another canonical operator, which is sometimes called the twisted partial operator, which is defined in this way. So it's denoted by delta j, and this is given by j to the minus 1 d bar j. Since again I and j anticommute, this operator goes from lambda rs I to lambda r plus 1 s with respect to I. Okay, and the way these two operators satisfy some relation similar to the operator d and d bar in complex geometry. So we have that d square is the same of dj square, and it is 0. And we have that they anticommute. Okay. And so the starting point for having a pluripotential theory is the local DDJ lemma, which states that the Hkt4 can be always written locally as DDJV for some potential v is a real function. Okay, so it's a real function defined, of course, not over M, but is just an open set of M. Okay, this was observed by Banos and so on. Well, and so this brings to the definition of a quaternionic plurisupermonic function. So a function phi in say infinity of M is quaternionic plurisupermonic if omega plus ddj phi is positive in the sense I described before, and this form is automatically Q real, and so this implies that the form omega phi, which is equal to omega plus ddj phi, is a new Hkt structure. Okay, so we start with an Hkt metric. In Hkt metric, we consider the induced form omega, and then by using a potential, we construct a new Hkt form, and now omega phi induces a new Hkt metric, G phi, which is Hkt. Okay, and now we can consider the analog of the bot-Chern class of omega. So we consider something I just call the class of omega. This is given by omega plus ddj phi. So such that phi is smooth function on M. Okay, and so the natural question, so the first question is if is there any canonical Hkt metric in this fixed class. So where canonical, of course, means some special, and the special here is from the viewpoint of the torsion of the geometrical structure. So this is the first natural question, and well, the second question, which is straight related to this question, if is there any Hkt form? Okay, I call it a Hkt metric by identifying the form with the metric in omega, which is balanced. So here I will call that Hermitian metric. G is balanced if its fundamental form omega is distal closed. Okay, so here the situation is the following. I have omega. I consider omega plus the dj phi, and this gives a new form of omega phi. And I ask if I can find phi such that the induced G phi together with the first complex structure is balanced. Okay, of course, one can consider the same question with other class of Hermitian metrics, for instance, pluriclosed. But at the beginning, the requirement of the balance condition seems to be more natural because, for instance, on Nil manifolds, what happens is that there are always Hkt metrics which are also balanced. Okay. And this question are posed by basically by Alasker and the Verbitsky. Okay, and it's quite easy to find an obstruction to the second question. And I mean, the Verbitsky proved the following. So let G be an Hkt balance metric. Okay, so a metric which is at the same time Hkt and balanced. Then, if we consider its induced form capital omega, and if we consider its top power omega to the n when n, where n is the quaternionic dimension of the manifold, we have that this form is holomorphic. So actually, these two. So actually, if we consider an Hkt metric, this metric is balanced if and only if omega to the n is holomorphic. So this is the real statement. And so this gives an obstruction for the existence of the balanced Hkt metric. So we have an obstruction. So if we consider Mij hypermission, and it admits a balanced Hkt metric, then Mij is SLNH. Okay, which since it is Hkt means that the canonical bundle of Mi is holomorphically trivial. Okay, so this is the first obstruction. So the answer to the second question is not always. There are obstructions. So maybe the second question can be improved with the third question, which is.
Sorry, is the uniqueness known in a class?
I say in a minute, but yes, there is the uniqueness. So I mean, there is a conjecture which states that if the canonical bond in the SLNH case, in this class, there is a unique Hkt balance metric. That's the conjecture I want to describe. So the question 3 is the following. Let Mij. So let Mij be a SLNH Hkt manifold is where any of course compact. So every time I forget to say compact. So I want also compact. as compact Hkd manifold. Is there any balance Hkt metric on Mij? Okay. So about this question 3, there is a conjecture which is given by Alaskar and Verbitsky. Which is the main open problem in Hkd geometry. Which is the following: consider Mijkg compact SL and H Hkt. Then in the class of omega, there is a unique balanced Hkt metric. Okay, so yes, there is. So it's true. I mean, the uniqueness is proved while the existence is not proved yet, but there are some partial results which I'm going to describe. So this is considered like an analog of the Calabi conjecture in Hkd geometry. And I describe a little bit the strategy. Okay, the strategy is the following. I mean, the strategy consists in reducing the problem to a partial differential equation as usual. And in order to do this, we have this assumption. So this assumption implies that Kmi is holomorphically trivial. Okay, is holomorphically trivial, so we can consider eta which is a holomorphic volume 4. Okay, and then we consider this equation: omega plus ddj phi to the n is equal to eta. Okay, and if this equation has a solution phi, then omega phi is balanced since eta is holomorphic. Okay, so if phi satisfies this condition, then omega phi is balanced. Okay, and starting from this condition, we can find, an obstruction. So by integrating in the usual way, so we start from this equation. Okay, and then we consider the wedge product with eta bar. And then we integrate. Okay. Okay, but since eta is holomorphic, we get that. We get that omega to the n wedge eta bar is the same of eta wedge eta bar. And now we can write eta as e to the f omega to the n for some f smooth function on m. Okay, and so this equation together, this obstruction can be written in this way. So we have, so the first equation is omega plus ddj phi to the n equal to e to the f omega n. So the second condition is positivity condition on phi. So omega plus ddj phi positive. And the last one is the compatibility, which can be written as the integration of e to the f minus 1 times omega to the n, which eta bar equal to 0. Okay, and this system is usually called the quaternionic motion pair equation. Okay, and I use this, I call this by QMA. Okay, so so the conjecture can be restated by saying that this equation has always a solution. So the equation can be, the conjecture can be restated in this way. So this equation has some nice properties. So the first one is that this equation is elliptic. Is elliptic, and maybe one of the main difficult in studying the equation is that usually it's not possible to use some special coordinates, and so if this equation is written in local coordinates, is something which is very, I mean, usually very involved. But well, what happens in the standard model is quite nice, because in the standard model which is given by h to the n, which is identified with. So here is possible to consider some, they are not coordinates, but they are called quaternionic coordinates. So we have these operators, Q alpha bar, which is given by the x for alpha plus I, the x for alpha plus 1 plus j, the x for alpha plus 2 plus k partial x for alpha plus 3. And then, so here I, j, k are quaternion numbers. And then we have another derivation, which is given by, without the bar, and is given by the x for alpha minus the x for alpha plus 1 I minus the for x for alpha plus 2j minus the x for alpha plus 3k. I mean, these are fault-like derivations, and even if they in general do not satisfy the Leibniz rule, but what is good is that they commute. Okay, and then if we write the quaternionic motion pair equation in this special case, we have the analog of the complex motion pair equation when it's written locally. So this is given by the determinant of the identity plus the matrix given by so partial q alpha partial q bar beta. So this is analog to, so these are, I mean, up to a constant. Okay, so in this local model, the equation is similar to the complex Moore-Ampere equation, but I mean, it's not possible always reduces the problem to this to the model to the to the local model. Okay, and what is known? Is known that the uniqueness part of the conjecture is proved. So where is the conjecture? Here. So here the uniqueness part is known and the existence is still open. And of course, the natural approach consisting in using the continuity method and doing some a priori estimates. And so far, people prove the C0 a priori estimate. So it's known that the solutions to the quaternionic Moore-Ampere equation satisfy a C0 a priori bound. So this is, I mean, the C0 estimate is completely understood and it is proved in 3 different papers. The first one by Alesker and Verbitsky. I mean, the second one is a paper of Alesker and Shelukin. Okay, and there is a more recent paper by Zrock. So, and I mean, the C0 estimate is proved in more generality, paper by paper. So in the paper of Alex Verbitsky, there are some restrictions, and then the paper of Alesker, there are some generalized. The previous one, the paper of Zrock is completely general. So the C0 bound is understood, while the other a priori estimates are understood, but by assuming some extra assumptions. And one big step is a theorem of Alesker, where actually the conjecture is proved by considering some extra very strong assumptions. And term is the following. So let I, J, K, G be a compact SL and H Hkt manifold. So these are the assumptions of the conjecture. And then there are the extra assumptions. So the first extra assumption is that the manifold is also locally flat. Okay, which I remember means it's locally isomorphic to the standard model. And there is also another assumption, and there exists a compatible hypercalometric. Okay, and of course the induced form of the hypercalometric is not in the class of omega. Otherwise, there is no statement. But this is hypercalometric is compatible with IJK, but is not in the class of G. And I mean, the term of Alesker is under this assumption that the conjecture is true. So in this assumption, then the quaternionic Moore-Ampere equation has a unique solution. Can be solved. Okay, and I mean, and the proof is obtained in two steps. So actually, usually is obtained in two steps. There is the C0 estimate, and then there is the C2 estimate, and then there is the C infinity estimate. But of course, the C0 estimate is dropped because it is already known. So there are also only two steps. So the first step is the upper bound of the Laplacian of the solution. Okay, and so this is the first step. And in order to prove this, all the assumptions are used. Okay, and then there is the subsequent step, which is consistent in showing that from this upper bound implies that Ck a priori bound for phi for every k. And here, not all the assumptions are used, but it is used only the local flatness. So the local flatness is used. Okay. So in particular, this assumption, the existence of a compatible hyperkähler metric is used only in this step. Well, while the second step is more general. And very recently, Dean Evans-Roca generalized Alasker theorem, removing this assumption, removing the local flatness. So very recently, there is this theorem of Dean Evans-Roca. So say so they removed the assumption locally flat from Alasker theorem. Okay, I think this is the more general result known about this conjecture, and the conjecture is in its generality is still open, and I'm trying to have some result in the opposite case with respect to Dean Evans-Roca. So by keeping the locally flatness and removing the assumption of the existence of a compatible hyperkähler metric. But I'm still.
Can I just ask a question?
Yes.
I think I maybe missed the point a little bit. Like, so you have this Hkt manifold SLNH.
Yeah.
The local flatness hypothesis is a assumption for like the given G, basically. Or it's.
No, the local flatness is assumptions only on the IJK, yes,
okay.
not related with G.
Okay, sorry, yeah.
So it means that MIJK is locally, so it means that it's possible to find coordinates which are holomorphic with respect to I, J, and K.
Okay, yeah.
And this is not something which it is related by the metric G.
Okay, yeah, thank you.
Okay. Okay, and now I want to describe a little bit some study that I did about this conjecture, and I started by studying the conjecture in some explicit examples. So I started to focus the conjecture on torus bundle. So the equation on on torus bundles. So I think since the problem in its generality seems to be very involved, I think it's, I mean, could be a good idea to try to see what happens, some explicit examples in order to increase the feeling with the problems. So I started to see what happens on the manifold, and I started from the three examples given by Dotti and Fino. So I focused on Dotti Fino examples. And I remember that the three examples are in dimension 8. Dimension 8, and are given as G mod gamma, where G is the potent. What happens is that all the examples are principal torus bundle over a torus. So I call this M. So all the three examples have this structure. So T3M over 85. So I focus on the equation when the datum F is T3 invariant. So what happens in this situation? Of course, we can use the ansatz that the solution is also T3 invariant, and in this way we have an equation which is an equation on the 5-dimensional torus, so which is more manageable than the original one. And so under this assumption, we reduce the equation to the following one on the 5-dimensional torus. We have 1 plus the sum for it, which goes from 1 to 4 of phi I. So we got something like this. So times 1 plus phi 5 minus the sum of I, which goes from 1 to 5 of phi 1 5 equal to e to the f. Okay, we got this equation, and I mean this is an equation on the 5-dimensional torus. So this is an equation on the 5. Okay. So what is nice on this equation? This equation, of course, can be written as A, B, C. So it can be written as AB minus C equal to e to the f. What we have is that A plus B is equal to 2 plus the Laplacian of phi. And this relation really helps in the a priori estimates. So the theorem we proved, the theorem I proved with Giovanni Gentili, with a PhD student in Torino, is that the quaternionic Moivre equation on M, which here by M I mean this class of manifolds, is solvable for every T3 invariant function f. Okay, so this is wants to be like a first step to understanding the equation in its generality, and in this example, in this class of examples. And it is like we are at the first step at the beginning. And now what we'd like to do is, of course, removing the symmetry from the datum and try to have something which is more general, or at least allows us to understand the equation in these examples. Well, and after that, we try to study the equation in its generality by using as quite natural a parabolic approach. So we introduced the parabolic approach. So, and we introduce what we call the quaternionic, the quaternionic parabolic Monge-Ampère equation. So, of course, the starting point consists by considering this is a perfect analog to the Keller case. So we consider the equation. Okay, what is maybe natural to do by having the Keller case in the complex and the Keller case in mind is to consider the geometric flow for studying this equation, and the most natural one is this one. So the time derivative of time-dependent function phi t is equal to the logarithm of omega phi t over omega phi t to the n over omega to the n minus f, where f is the datum, and and as initial phi we can consider the zero function. And so we call this equation the parabolic quaternionic parabolic Monge-Ampère equation. And of course, the natural conjecture is that these flows, once normalized, always converges to something which solves the original, the quaternionic Monge-Ampère equation, which is a sort of a generalization of the Alexander and Verbitsky conjecture. And actually, we confirmed this conjecture under the same assumptions of Alexander theorem. So our result here, which obtained with Bedulli, Gentili, and me, is that in the same assumptions of Alexander theorem, the quaternionic parabolic Monge-Ampère equation as a long-time solution. Phi t with t 0 infinity, such that phi t, once normalized, converges for t which is close to infinity to phi infinity with phi infinity solution to the quaternionic Monge-Ampère equation. Okay. Also, I mean, also in this case, the proof can be subdivided in steps, and well, not in all steps we need the assumptions, but all the assumptions are needed only in the C2 upper bound. I describe a little bit the idea of the proof, and especially I'd like to show how we got the convergence, because I mean, from the proof of the convergence, we deduced another geometric flow which can be interested in, I think, which can be interested in Hkd geometry. So, the idea of the proof. So more or less the proof can be subdivided in 5 steps. So the first one is almost immediate, consistent given a C0 bound. For the time derivative of phi t, and this is general. Well, when I put general, I mean that I don't have to use the local flatness and the existence of an underlying hyperkähler metric. The step 2 consists of giving a bound for the oscillation of phi t, and this is again general. Okay. Well, the step 3 is where we use all the assumptions. So the step 3 consists on giving an upper bound to the Laplacian of phi t, and here is where we need all the assumptions. Okay. The step 4, we deduce the C infinity a priori bound for phi t, and here we use the local flatness. So in particular, in this step, we don't need the existence of an underlying hyperkähler metric. All these assumptions together give the long time existence. Okay, so the remaining step is the convergence. Is given by the convergence. So, and about the convergence, we adopt an argument of Von Sturm, which consists in, well, Von Sturm used this argument for the convergence of the parabolic for the Kähler-Ricci flow by combining the Kähler-Ricci flow with the Calabi flow. So we use we adopt this argument, so we consider Hkt given by the integration of the logarithm of omega phi t to the n modulo omega to the n omega phi t to the n omega wedge eta bar, where eta is still holomorphic volume form, minus the integration of f of omega phi to the n wedge eta bar. Okay, and what happens for this f is that the second derivative of ft is greater and equal of a uniform constant for the first derivative of f respect to t. And from here, it's not difficult to show that the limit for t goes to infinity of the first derivative of f is 0. And from here, we deduce the convergence. Of the normalization of the solution. So phi of phi t minus the integration of phi t. So I mean, this is quite standard argument in order. Or I mean, this is in general. We don't need any of the extra assumptions. This is I mean, this also is quite standard, but this is suggested to consider an analog of the Calabi flow in the context of Hkt geometry, and this is still in progress. So.
Sorry, what role are you saying Calabi flow plays in this step 5? I don't think I understood.
Not really the Calabi flow, the Mabuchi energy. And I mean, this is a sort of a Mabuchi energy adapted to the Hkt geometry. And then by studying the gradient flow of the Mabuchi energy, we obtain something which is analogous to the Calabi flow.
Oh, I see.
I described this a little bit.
Sure. I mean, can you also just get the convergence by like a Liao estimate, I imagine?
Yes. Yes. But in some sense, I prefer this point of view because let me to motivate the study of the Mabuchi energy in Hkt geometry. So Mabuchi energy. This is still in progress. I mean, everything is still in progress, but this is at the very beginning. So here we start from M, I, J, K, G. As usual, you consider something which is Hkt and also S, L, and H. I mean, I take the omega to the n, and I consider its partial derivative, the bar derivative, and this can be written as one form theta bar wedge omega to the n. Okay, where this theta is a 104. With respect to I, and of course G is balanced if and only if this form theta is 0. So it's quite natural to construct a flow which I mean which is or a functional which is minimizing for this theta. Okay, and now it's possible to fix H as a smooth function such that if we do partial J theta bar is given by djh by using an analog to the dd bar lemma in Hkt geometry. Okay, and then I consider the set H of Q pluri-subharmonic functions. So our smooth function on M such that omega phi given by omega plus dj phi is positive. And of course here, and then I consider what is for me also a fix eta holomorphic volume form. Okay, and then I introduce what is the analog of the Mabuchi energy in this setting, which is given by m phi equal to the integration of the logarithmic of omega phi to the n over omega to the n, omega phi to the n, omega wedge theta bar minus h omega phi to the n wedge eta bar. And it's not difficult to show that if phi is critical with respect to n, then omega phi is balanced. Okay, and so it's interesting to study the gradient flow of this energy. And what happens about the gradient flow? The gradient flow is given by this flow. Time derivative of phi t is given by the stuff is given by j of d bar j theta phi wedge omega n to the minus 1 phi. This everything depends on over omega phi t to the n. This is something I called S of phi t because it reminds me the Calabi flow in Hkd geometry, and so I got this flow. Which is analog of the Calabi flow. In Hkd geometry. Okay. So now I'm a little bit motivated to understanding the analysis and geometry of this flow, and to see if it's possible of using this flow in order to have some advances in the conjecture. So here is, I mean, this is very at the beginning of this in this research project. And if I have also, if I still have 5 or 6 minutes.
Sure. Yeah.
Yeah. So I'd like to, describe, another open problem in Hkt geometry. I've not worked in this one, but maybe I think it's interesting, and it's the problem about existence, or something that people call strong Hkt matrix. Well, and the strong Hkt matrix, so the definition is very easy, and start from an Hkt G, and here the request is that is G is Hkt and pluriclosed. So, and the feeling is that this pluriclosed, of course, with respect to I. So, and the feeling is that this request is very restrictive, and it's, it's a very versatile. There are some examples, but I think the only known examples are in the class of Joyce examples, and I think these are the only known examples. And what Verbitsky proved is that in omega, in the class of omega, there is a balanced Hkt metric and also a strong Hkt metric. Then there is also a hyperkähler metric in the class. What happens is that if the manifold is not hyperkähler, it's not possible to find a balanced Hkt metric and also a strong Hkt metric. And this is this open problem, which is a conjecture, still by Verbitsky. I mean, the statement seems to be easy, but I don't know how to prove it. The conjecture is the following. In this class, there is at most one strong Hkt metric. So also this is still open, and as far as I know, is not proved yet. And of course, if one assumes the conjecture of Alesker and Verbitsky, it is not possible to find a strong Hkt metric on an SLNH Hkt manifold. Okay, I think I can stop here, and I said more or less everything I want to talk about. So thanks a lot for your attention.
Yeah, thanks, Luigi. That was a very nice talk.
Thank you.
Are there other questions?
Luigi?
Yes, ciao Anna.
Now I put the video. So
yeah,
just a remark, I don't know if useful or not. In the case of strong Hkt manifolds, there are not only the Joyce example. With Laura Barberis, we found an 8-dimensional example which was strong Hkt and was a semi-direct product of something which is like SU2, semi-direct product with F4, and then you have an extra factor. So it's not of that type. So I don't know what happened in that case.
But is this examples compact?
Yes, he has a compact version.
Yes. That's interesting. Sorry if it's missed.
Is in the paper with Laura Barberis and Matt Chris, and is described. I mean, we is a product 7+1. So in the 7-dimension there was a different type of structure related to generalized to structure, whatever. But I think maybe it's, I don't know. Yes, it's an example which is not in that class that you mentioned.
Okay, thanks for the remark.
Can I just ask, is this space of possible cohomology class, or I mean like this cohomology class of omega, it's a finite dimensional space, all possible bracket omega?
I think it's... I think it should be finite dimensional. I think so. I think it should be some finite dimension. Yeah, yeah.
So like there shouldn't really be, I mean, in any case, if this conjecture is true, then like there's really like no flexible construction of this Hkt metrics. Like there's no possibility of like a potential theory or something like that, or like some large space of perturbations, I guess.
Yeah, but I think it should be finite dimensional because it's yeah, you can use an argument similar to the yeah, you can use something like the, I mean, it's possible. I think it's, I mean, I'm quite sure it's finite dimensional.
Yeah.
So I have also one question, if it's okay. Can you hear me?
Yeah.
Yeah. Hi, Luigi. So this main existence conjecture, which you mentioned. So it's assumed that the manifold admits some balance metric, or does it follow sort of a posteriori from the conjecture?
No, it follows a posteriori.
Okay, so it's not assumed, and it's kind of not clear in advance, right, whether balance metric exists.
No. It's, I mean, it's something which is a posteriori. Yes. I mean, you don't have the assumption the manifold as balance matrix, admits balance matrix. It's something which is implied by the conjecture.
Right. Okay. Yeah. Right. Thank you.
Okay. Other questions? Okay. If not, yeah, let's thank Luigi again. That was a very nice talk.
Thank you.